Okay. Hello everyone, my name is Ghelmani. I'm a PhD student at Concordia University doing research under the supervision of Professor Amin Hammad. Today I will be presenting our latest research titled Enhancing Single-Stage Excavator Activity Recognition via Knowledge Distillation of Temporal Gradient Data. This is the agenda of my presentation that goes from problem statement to methodology and finally experimental results and conclusions. And traditionally, construction site metering has been performed manually. However, manual supervision is time-consuming and error-prone, especially on large construction sites. So over the years, many automated methods have been developed, and most of the developed automated methods are vision-based because of advantages like prevalence of surveillance cameras on most construction sites. Surveillance cameras are usually installed at high altitudes and can provide a wide monitoring range, and also by using methods developed in the field of computer vision, many high-performing methods have been developed in construction domain as well. Most of the current activity recognition methods are multi-stage, like this work that we see proposed by one of my colleagues. In this method, they use the faster RCNN network to detect the equipment in each frame. After that, the detected equipment were tracked in consecutive frames. And to further improve performance, they also crop the frames around each of the detected equipment. And finally, they use the 3D result network for activity recognition. They also do a processing based on the center point of the predicted bounding boxes and the standard deviation of their area to find the idling state of the equipment. In this video, we can see a sample output of their method for two excavators, and they use the result of activity recognition and idling state to estimate productivity, as we can see in this table for the two excavators in the video. However, this method has two disadvantages. The first is that the errors from earlier stages will propagate through the model and the overall performance will suffer because of that. And the second is that each stage needs a separate processing time and also a separate training time, so the overall inference speed is relatively low. To solve this problem, another one of my colleagues proposed a single stage method for the construction worker activity recognition with the name of YOVO, for You Only Watch Once. In this method, they use a 3D CNN backbone to process the input videos and a 2D CNN backbone to process the final frame of the input video to provide more accurate localization information. After that, they combine the output of the two backbones using a channel fusion and attention module, which is then used to produce the final output that we see in this figure. And we can see some sample videos from this method in this slide as well. However, this method has one problem, and it's that it has relatively low per frame performance. So to obtain acceptable accuracy, they need to link the per frame results, which can be time consuming depending on the number of frames in the video and the number of detections per frame. To solve this problem in this work, we propose DIGGER, which stands for Knowledge Distillation of Temporal Gradient Data for Construction Entity Activity Recognition. Our method has three main components. The first is the original YOVO method that we're trying to improve. The second is the added temporal gradient backbone and knowledge distillation component. And the third is the complete intersection over union loss and the Gaussian soft non-maximum suppression technique that we have added to improve localization accuracy. However, because of time constraints, I will not explain the Gaussian non-maximum suppression technique in this presentation. Temporal gradient is obtained by calculating the difference between two RGB frames, and as you can see in these figures, temporal gradient mostly has dynamic information, and most of the spatial information is removed because of the difference operation. So potentially including this data modality can help with improving the activity recognition accuracy. And to use this data, we have added a third backbone to the original YOVO model to process and extract feature from this. And in the selection of this backbone, we have considered a few factors. The first is that not to have a large number of parameters that would then need a lot of data for training. The second is that we want this backbone to focus on the extraction of temporal information because the spatial information is already being extracted by the other two backbones. And a third factor is that recently some works like the slow fast network that we see in this figure have proposed to a stream architecture in which they use a smaller backbone alongside the bigger one, so that the smaller backbone can focus on the extraction of temporal information. For example, in here they input the high temporal resolution data to the smaller backbone so that it can focus mostly on the extraction of temporal information, while the bigger one focuses on the extraction of spatial information. Inspired by this, in this work we have selected these two networks for the temporal gradient and RGB backbone. And as you can see, the number of parameters of the temporal gradient backbone is approximately 1/10 of the RGB one. To train this backbone, we have adopted an approach similar to the original YOVO method, and that is we train it alongside the 2D CNN backbone and the CFAM module. We have selected this approach because we want potentially the 3D CNN temporal gradient backbone. No laser pointer, sorry. The 3D CNN temporal gradient backbone and the RGB backbone to extract the information, different modes of information about the same semantic data. So we want to avoid the difference in the training to result in difference in the extracted data. And I also mentioned that the 2D CNN backbone is mostly used to improve localization accuracy. So we want to avoid it being like being affected by the temporal gradient data, which is mostly dynamic information. So in this step, we use a stop gradient to stop degrading the 2D CNN backbone by this data. The main problem with using multiple data modalities is that when you use multiple data modalities, there is increased computation demands that leads to a slower inference. To solve this problem, in our work, we have adopted knowledge distillation. Knowledge distillation refers to the transfer of knowledge from a typically bigger and more complex teacher model to a smaller student model, with the aim of improving the performance of the student while you keep the computational efficiency of the student network. Some works like the Distilled 3D network have used knowledge distillation to transfer knowledge from different data modalities, for example, from optical flow to the RGB one. In our work, we use knowledge distillation to transfer knowledge from the temporal gradient backbone to the RGB backbone. And I mentioned that we're using knowledge distillation to solve the problem with added computation, but how is this helping? We use knowledge distillation during the training to improve the performance of the RGB backbone by transferring knowledge from the temporal gradient data. So during inference, we will drop this added backbone. So overall, we obtain improved performance at no additional computation cost. And to perform knowledge distillation, the most common approach is to reduce the difference between the output of the teacher and student networks. And however, recently Jiao et al. Have shown that instead of just using the final output, if you include earlier layers, it leads to better knowledge transfer. So in our work, we have also adopted a multi-layer approach to knowledge distillation. To perform knowledge distillation successfully, we had to consider a few factors. The first is that to reduce the difference between the output of the layers, they need to be of the same size. However, if you remember, we selected the temporal gradient backbone to be smaller. So we needed to use a lateral connection module to align the output of the RGB backbone with the TG backbone. However, there is still another problem because the earlier layers that we have included in knowledge distillation have high dimensions. And to perform knowledge distillation in this high dimensional space would need a lot of data, otherwise the training would not converge. So we use a multi-layer projection to map the output of these layers to a lower dimensional space to make the transfer of knowledge easier in this smaller space. Finally, we want, during knowledge distillation, we want the knowledge to transfer from the teacher to the student and not the other way around, because then it will create a degenerate loop. So in this step, we use a stop gradient again to stop the transfer of knowledge from the student to the teacher backbone. The final component of our work is regarding the localization improvement. And original YOVO method uses a smooth L1 loss for localization, which has two disadvantages. The first is that it considers the coordinates of the predicted bounding box separately, and it does not optimize it as a whole box. The second is that during testing, we usually use the intersection over union metric, which measures the overlap area between the two boxes. So there is difference between the localization metrics that are used for training and testing. To solve this problem, in our work, we have used the complete intersection over union loss, which not only includes the IOU, but also reduces the normalized distance between the center point of the two bounding boxes, and also reduces the difference between their aspect ratios. So overall, it leads to better alignment between the two boxes. To test the performance of our method, we have tested the performance of our method on a large custom dataset of Excavator activities. Our dataset has more than 1,000 videos of the 3 activities of digging, swinging, and loading. In the figure, you can see some sample images from our dataset that has different lighting, weather, and camera angle conditions. In this table, we provide a performance comparison between our method and the original Yovo method. The classification accuracy metric measures the activity recognition performance of the methods. The localization, recall, and precision measure the recall and precision in predicting bounding boxes. And the mean average precision metric measures the quality or the accuracy or the alignment of the 2 boxes. Overall, we see that using our method leads to 5.7% improvement in activity recognition, 7.8 and 7.9% improvement in localization, recall, and precision, and more importantly, 8.4% improvement in the accuracy of the localization. I mentioned that the intuition for developing our method was to reduce the need for video level processing. So we also present the result of video level processing in this table. As you can see, in both cases, the performance improves when you do video level processing, which is expected because you're processing all of the frames together in this case. However, in the original method, there is a 13.3% difference between the per frame and video level results. While in our case, this difference has been reduced to only 5.5%. Also, our method has close to 80% per frame localization accuracy, which can be accepted for most applications, and only for some applications like safety that you need high localization accuracy, doing the time-consuming video level processing might be justified. So overall, in our work, we have used temporal gradient and knowledge distillation for activity recognition of construction equipment. Our method has the per frame accuracy of close to 80% localization and 93.6% activity recognition accuracies. We have reduced the difference between the per frame and video level results at no additional inference cost. And the future work for our work can be extending its abilities to extract activities of multiple equipment at different scales. Thank you.